Okay, well, hi, my name is Thankful Cromartie. I just defended my PhD at the University of Virginia this spring, and I'll be starting as an Einstein postdoc at Cornell in about a month. So today I'd like to talk to you about two very interesting millisecond pulsars and some radio Shapiro delay observations we've been conducting for them. So I'm going to zoom through some basics here. Millisecond pulsars are a subset of the larger pulsar population. They are extremely rapidly rotating neutron stars that are a very old population, most of which are in binaries. They have relatively weak magnetic fields. They're still quite strong. And we know of just over 300 of them, whereas we know of about 3,000 normal pulsars. So pulsar timing, the reason we love millisecond pulsars is because they're great for pulsar timing. They spin down very slowly. So the process of pulsar timing is unambiguously accounting for every single rotation from one of these objects. And if we can create a model that predicts each and every arrival time of each pulse, we know that if the pulse arrival time we measure doesn't match up, then there's some intervening factor going on. You know, things like the ISM, GR effects, all kinds of things can cause discrepancies in the measured and predicted times of arrival of these pulses. We call those timing residuals. You can see in the bottom panels, the top panel shows you when your model is looking good, you're accounting for everything properly. You've got those, really nice spread of the residuals around zero, not too much structure or anything. If you're missing a parameter, for example, like proper motion, you can introduce structure into your timing residuals and you know that you're missing something. So this research is being conducted within the context of the NanoGrav collaboration, the North American Nanohertz Observatory for Gravitational Waves. And the goal of that collaboration is to detect a low frequency stochastic background of gravitational waves from supermassive black holes. Our program consists of monthly dual frequency observations of more than 75 millisecond pulsars. And we're currently working on our 15-year data set. So we've been at this for a while. We primarily use the Green Bank and Arecibo telescopes, but we're also incorporating VLA data and CHIME data into our data set as well. So the NanoGrav data set is extremely rich for secondary science pursuits, and I'm just going to talk about one of them, but there are all kinds of interesting things you can do with our data. But what I'll be talking about today are mass measurements of neutron stars. So relativistic Shapiro delay observations of J0740 plus 6620. The reason why we care about making these kinds of mass measurements is because it can help constrain the really poorly understood neutron star interior equation of state, so the way matter behaves at supernuclear densities deep inside neutron stars. And one of the really nice things is that these equations of state are translatable into observable parameters. So you can see on the right this mass versus radius diagram, how all the equations of state behave in that space. And what this means is that by observing more and more massive neutron stars, more and more massive pulsars, we can rule out certain equations of state because each one has to account for a neutron star that is as massive as the ones we've observed. But the question is, how do we measure them precisely? And one really great way to do so is by looking at relativistic Shapiro delay. So normal pulsar timing of binaries yields 5 Keplerian parameters, things like binary orbital period, eccentricity. But in a very small subset of systems, we can measure a general relativistic effect called Shapiro delay. And that's what happens when, most of these are white dwarf millisecond pulsar binaries that we're looking at. And so when the pulsar goes behind its companion at superior conjunction, the companion's deformation of space-time causes the pulses from the millisecond pulsar to arrive later than we would have expected otherwise. And so the Shapiro delay can be characterized by two parameters, post-Keplerian parameters range and shape, and those are directly measurable. And then by combining them with mass function, we're able to get out independent measurements of the pulsar's mass as well as the companion's mass. And so that turns out to be an extremely powerful tool for getting precise neutron star mass measurements. So here's a little toy model of what Shapiro delay looks like. We define superior conjunction as occurring at orbital phase of 0.25. You can see that the Shapiro delay peaks at superior conjunction. It's this very spiky shape. And you can also see that it's extremely dependent on the inclination angle of the orbit. And so by looking at the different shades of blue there, you can tell that even the difference between, an inclination of 80 degrees and an inclination of 89 degrees makes all the difference in the world. So this effect isn't visible all that often. You have to have a really highly inclined system in order to measure it precisely. So let's see. Quick history of neutron star mass measurements. For a long time, it was thought, the canonical model of a neutron star had its mass at about 1.4 solar masses. But then in 2010, Demarest et al. Reported the first 2 solar mass neutron star through Shapiro delay observations. And that was a really revolutionary paper. It changed the way we thought about neutron stars in a pretty serious way. Antoniadis et al. In 2013 measured yet another more massive neutron star. And then more recently, these constraints can be made in other ways as well. So the LIGO double neutron star merger was really great in putting an upper limit on neutron star masses. And we think that to be about 2.17 solar masses from those measurements. So JO740 plus 6620 was discovered in the Green Bank North Celestial Cap survey in 2014 and was very shortly after added to the nanograv pulsar timing array. It showed after about 4 years of observations a small hint of Shapiro delay. And so we actually proposed to look at this source and several other sources over superior conjunction to see if we could refine that mass measurement. And after the first supplemental campaign, these targeted phase observation campaigns, we saw that it indeed looked like it was probably a massive source with a mass measurement of 2.18 plus or minus 0.05 solar, or 1.15 solar masses. Important distinction. So this wasn't a particularly good constraint, but it was enough to make us take a serious look at it and think that we really needed to refine this mass measurement further. So what you see on the left is just a simulation of, this was just how we tried to figure out what the best observing strategy would be. And we use this information to motivate a director's discretionary time campaign with GBT to get 10 more hours of Shapiro delay observations. And so the green is just the kind of nominal Shapiro delay curve. And then the black shows the improvement in the 1 sigma error bars on mass you get by conducting a 5-hour observation over each point in the orbital phase. And so what you see is kind of what you would expect, which is that by sampling both the peak and the trough of the Shapiro delay curve, you're able to get the best possible refinement of the mass. That makes logical sense. You would think that you want to sample the entire curve, but it was good to have an actual validation of that. And so we were awarded 10 hours, 5 of which we observed over orbital superior conjunction, and then 5 of which we got in one of the Shapiro delay troughs, and it helped us significantly refine our mass measurement. And so by combining all the nanograv data that we had for this source with the first and second targeted observations, we find in the end that the mass of this pulsar is 2.14 plus or minus 0.09 solar masses, and that was reported in 2019. The plot on the right, the 3 panels show you, the top panel is what your timing residuals look like when your model is accounting properly for everything. The second is the signal that we're actually sensitive to. So that's, what we can detect without knowing the mass of the companion and the inclination angle a priori. And then the third panel is the full extent of that Shapiro delay signal. So what does this mean? Higher mass neutron star measurements require stiffer equations of state to explain. And so that means that this was kind of in tension with the non-nucleonic proposals, things like quark matter and hyperons and Bose-Einstein condensates. There's still a lot of problems, obviously, in the world of neutron star equations of state, but this helps us learn a little bit more. You can also see from this plot that we really do need to refine our mass measurement a lot more. Unfortunately, these kinds of targeted campaigns over conjunction produce they're not so productive over time. It's diminishing returns for sure with observations like that. But we were able to add in daily observations using the CHIME radio telescope, which have been extremely important for refining the mass. And this is actually really exciting because the NICER collaboration, this source has X-ray pulsations, and so their light curve modeling is going to be really important for constraining the equation of state. And they're able to use our measurements of, mass and parallax and other things as priors in their light curve modeling. And so hopefully this will produce a really nice result for NICER. It's a funny thing to say, but currently when we combine all of our radio observations, including GBT and CHIME, our mass constraint is about 2.13 plus or minus 7 solar masses. That's a rough number, not finalized. But this is all going to be reported in 2 forthcoming publications on both the radio and X-ray side. So it's really good. It's good news that we're still producing a result that's very much in agreement with our original publication. So we're excited to see where this goes. So secondly, I'm going to talk about multi-wavelength observations of another millisecond pulsar, J1231 minus 1411. So this source was discovered in a search of follow-up observations of Fermi unidentified sources using the GBT in 2011. It's one of the main targets of interest for NICER, but it's also, interestingly, the brightest MSP we know of in gamma rays. And we have a lot of Fermi data that we use in this analysis. Looking at the X-ray light curve, it shows a single dominant peak. It suggests that it might be a less massive source. We also think it's probably highly inclined. And we're doing a similar thing where we're able to use radio Shapiro delay observations in order to inform NICER's constraint on the mass radius ratio and constraining the equation of state. So we obtained 22 additional hours. There were already a long period of Millisecond observations, Millisecond radio telescope observations for this source, as well as some initial GBT observations. And so by combining those with 22 additional hours using the GBT, which included 2 6-hour conjunction phase observations, we're able to get a nicer constraint on the mass. So we do this modeling in a couple different ways. Using kind of typical pulsar timing software, we can grid over the inclination angle and companion mass measurement, and we end up obtaining a mass for the pulsar that's quite low, 0.75 plus 0.55 minus 0.3 solar masses. That's 1 sigma confidence interval. And obviously, we know that this source is not a 0.75 solar mass neutron star, but it does suggest that it's probably a very low mass neutron star.
2 minutes. 2 minutes, thank you.
Okay, perfect. Yep. So then we also conduct MCMC fits for this source. Pulsar timing with Bayesian techniques isn't super popular, but it is coming into vogue. We wanted to have some, physically informed priors on the companion mass and the inclination angle. And so we end up using the Torsen-Savonage 1999 relationship between white dwarf mass and orbital period in order to center our prior on the companion mass at a value that makes physical sense. And we also use a flat in cosine I prior on the inclination angle to simulate a basically random distribution of orbital inclinations. And so you don't need to look at that plot. That's just all the parameters we're fitting for. But we ran 6 different trials using different priors on the companion mass. And what we find is that the companion mass really is informative. You can see how it is kind of breaking through the prior in that top panel. And we find a very similar mass measurement for the neutron star, 0.78 solar masses-ish, with a slightly narrower error bar. But this again is suggesting that it is a very low mass source at a high inclination angle. And so what's interesting is that companion mass is informative, but it ends up being much lower than what the TS99 relationship would suggest, or would predict rather. And so it's not really worrisome, but it is interesting. And it turns out that there are a lot of systems being found that don't 100% agree with TS99, but it's something that we're still looking at. And so the other thing to remember is that just because this isn't a very high mass neutron star doesn't mean that it's not extremely important for NICER's equation of state constraints. You need to be able to constrain the entire space. And so it'd be a mistake to just care about the high mass MSP measurements. And finally, we looked at the Fermi gamma ray data, 12 years of it. We're using a Bayesian single photon timing technique to do this timing and present results that are similar to those we get in radio. And unfortunately, what we end up finding is that the Fermi data aren't particularly constraining. And so those aren't helping us a ton in coming up with a good mass measurement and inclination measurement for the source. So that's all I've got. Thank you so much.
Okay. If we have any questions, you can enter them in Q&A. And just a reminder that you can enter your questions a bit early, if you have any. Okay, I will ask maybe one really kind of general question about the next big thing for millisecond pulsars. I'm guessing is SKA, right? Is that sort of the thing that's going to get you out of the 300 source range, or? Oh, you are muted. Sorry,
my bad. That's going to be extremely important. But there are other projects coming online. Things like Meerkat. Meerkat's been really, really important. Obviously, FAST has been great at finding new sources. So we don't have to just wait for SK, but that is going to be an extremely important project for us. That's certainly right.
Okay, we do have one question. Craig Heinke says, fascinating talk. Can you exclude that the companion mass of the latter source is consistent with the Taurus-Savigny relation at high confidence?
I mean, the 2 sigma error bars are still in agreement with TS99. So I guess no is really the answer. But it is interesting because certainly both our chi-squared analysis and MCMC analyses seem to suggest that it is much lower than what TS99 predicts. But I guess no, I mean, it's still consistent with TS99 on some level. It's something we kind of just have to pay more attention to. It's unfortunate that the Fermi data aren't helping us constrain that companion mass. That would have been a very helpful thing.
Okay, another question from Herman Marshall. Could you comment on using such timing data to constrain models of gravity?
Oh, so yeah, it's interesting. There are several different ways that pulsar timing can help constrain GR. One of the interesting things is the Nanograv project is actually able to test different gravitational wave polarizations, so things like that can be done. The possibilities are really, there are a lot of possibilities for testing GR with pulsar timing. There's some interesting things like, there's this triple system with 2 white dwarfs and a millisecond pulsar that's great for GR constraints. That's been providing some really fantastic results. And so, yes, it is possible, I guess. I'm not sure if that was the question, but there are lots of different ways to test GR with pulsar timing.